Well, we've hit noon, so we can go ahead and get started. I told Liddy, but we'll definitely have people, like she said, hitting the coffee pot, getting a little lunch maybe before jumping on. We'll have people joining us probably the next 10 minutes or so. But I just want to say thank you so much to everyone for attending today's Montana Institute on Ecosystems Rough Cut seminar series. We're very excited to have Dr. Elizabeth Meredith with us today. Just a little context on the IOE Rough Cut seminar series for those who maybe are attending for the first time. We have a weekly seminar series, the Rough Cut, and it brings together speakers from the Montana University system, state and federal agencies, nonprofits, and many other different entities to present on environmental and ecosystem science research and work that is being done across the state, really with the goal of enhancing statewide interdisciplinary activities and allowing us to really learn from each other and learn about what is going on. So just a few housekeeping items for everyone on today. You'll notice that when you've entered the seminar, you've been automatically muted. So we're just asking that you keep your mics muted throughout the seminar just to make sure we're not getting any noise interference. I'll also ask just for bandwidth capacity, if you are able to keep your videos off during the presentation. Sometimes WebEx can be a little finicky and internet can be finicky as well, especially with a lot of people online. So just ask if you're able to turn your videos off. I'll turn mine off during the presentation as well. For the question and answer period, again, during the seminar, we ask that if you have a question to please type that into the chat function. Again, just limiting any kind of noise interference while Liddy is presenting. And then at the end of her presentation for Q&A, you can either type a question into the chat function, or we found that unmuting yourself at that point has worked pretty well, helps increase that kind of interaction between people. So if you do have a question, feel free to do it either way, either chat or unmute yourself and ask the question again after her presentation is done. But during the presentation, please type into the chat box. And then just another note is that we will be recording this seminar and we'll post the link and the video on the montanaioe.org website. And I'll make sure to type that into the chat box so you know where to navigate to if you want to go back at a later point and watch this or share it with somebody that maybe isn't able to make it today. Just a note that we will be recording this. So housekeeping items out of the way, I'm going to go ahead and introduce our speaker for today. We're very excited. Like I said, we have Dr. Elizabeth Meredith with us today, and she is a hydrogeologist with the Montana Bureau of Mines and Geology and has been in that position for the past 13 years. And Dr. Meredith works on a range of eastern Montana groundwater issues, including impacts from coal mining, oil production, and agricultural salt mobilization. She says in her bio she spent a hot August week in Colstrip installing a series of wells for the NSF EPSCoR funded cruise project, and her presentation today will introduce the research questions and natural setting of the new study area. So I will go ahead and hand it over to you, Liddy. I'm sure you'll expand more on that hot August week that you spent installing wells, so thank you so much.
Yeah, I hope maybe some of the pictures give you a clue as to just how hot and dusty it was out there. The great thing about field work in eastern Montana is that from season to season you forget and you always agree to do it again. And so we always find ourselves out there, and in retrospect, it's always a good time. But that those 100-degree days push anyone's good humor limit. So yes, as Madison explained, introduced, I'm going to be talking today about the work that we did this summer in establishing a new research site in the Powder River Basin, and it's affiliated with the NSF Cruise grant. This is an EPSCoR funded grant through NSF to a consortium of a lot of researchers throughout the state. Almost every campus, I think, by this time is represented in this research effort. And so it's a wonderful opportunity for collaboration and just synergy and networking across research campuses. And it's been a great experience so far. So CRUISE stands for the Consortium for Research on Environmental Water Systems. And that's why it's kind of a mouthful and gets shortened down to CRUISE. The sign here speaks to the history of the study site. It was the Big Sky coal mine, and it was leased and was previously owned and then leased and now owned again by Greenleaf Land and Cattle Company, which are the landowners that we're working with and have worked with for many decades. A quick introduction. Let's see, is it moving? Can't seem to forward it.
It's not advancing. Maybe try refreshing. I don't know, clicking on the presentation itself. Sometimes it, I know.
Oh,
Yeah,
okay.
times out.
Yeah, maybe that's what happened. So, quick introduction to who I am and who I work with. Most of you, I'm sure probably all of you, are familiar with the academic side of the Montana University system. I mean, that includes MSU and U of M and all the affiliated campuses. But a lot of people may not also know that there's an extension side to the university system. And that includes on MSU's campus, you're probably mostly familiar with the Agricultural Experiment Station and the Ag Extension Service. But it also includes the Fire Service and Forestry Services out of U of M and the Montana Bureau of Mines and Geology, which is housed at Montana Tech in Butte. And so like the quick and easy explanation for who we are is it's the geologic extension for the state of Montana, and we provide geology and hydrogeology information in support of state interests. The less quick explanation is that we're a non-regulatory research bureau for the state of Montana and a department within Montana Technological University. And as such, naturally, the main office is there on the Tech campus in Butte. However, in order to address some of the important geologic, economic, and environmental issues in eastern Montana, and just because Montana is as big as it is, we also have a Billings office, which is where I work out of. And in fact, today I'm speaking to you live from beautiful Billings, Montana. With the advent of this wonderful video conferencing technology, we've all been forced to incorporate into our lives recently. So the Bureau began in 1919. It was established and provides geology and hydrogeologic information to assist in the orderly development of the state's energy, mineral, and water resources. Back to the CRUISE part of that research, CRUISE has three main focuses. It's focusing widely on how humans impact water systems in Montana, and specifically in three defined areas of that human interaction. And one being hard rock mining, looking at hard rock mining in the Butte Anaconda area and how that impacts the upper Clarks Fork River. Agricultural impacts are mostly focused on in a Judith River watershed study area, looking at nitrates that occur both naturally and through agricultural practices. And of course, the Powder River Basin is here listed under energy extraction, but clearly with Powder River Basin as a study site, we're really only talking about coal and coal mining. Within each of those study areas, the research is on three different scales. One, the one I have circled, and the little cell within this matrix that the work I'm presenting today falls within, is the environmental, the system scale of environmental research. However, there are people working at the molecular scale at all these sites. And also there's a sensor engineering side to how sensors can be incorporated into these environmental questions. And over all of that is the social science component of this and how humans both interacted with the environment to cause these disturbances, but also the science that the solutions that are researched and and expounded upon with this work can only go so far if you don't have the human component integrated into it. And so how do we work with the people in the areas in order to address some of these issues that we're looking at? So I'm just one cog in that whole system, and that's shown by the fact that only one of those little cells is circled here. More specifically to what we're looking at in the Powder River Basin is we're going to look primarily at sulfate and the sulfate system, because the coal mining, and in particular when coal mining is complete and the spoils refill the old mine site and it's reclaimed, the mobilization of salt is often in the form of dissolved sulfate salts. And sulfate is an important water quality parameter primarily for cattle. It's a drinking water standard. It's a primary drinking water standard for cattle. It's a secondary standard for humans. But in cattle, it can make them go blind, and it can kill them at high enough concentrations. And so this being a major agricultural cattle growing area, sulfate is a real concern. And so we're going to be looking at the mobilization of sulfate in these old coal mines, in these reclaimed coal mines, and seeing if we can trace the mobilization of that sulfate down gradient and see if it's interacting, and if we can trace and identify its interaction with the surface water system. So we know that coal spoils are a source of salt because the Bureau of Mines has been working in the coal strip area and in these major coal producing areas in Montana since the late 60s and early 70s. And just to back up and give you some history of coal mining and the process of strip coal mining, the overlying rock in this area is primarily sandstone and shales, but even some small coal zones are blasted, dynamite blasted out of place, and then they're removed and stockpiled for later, which allows access to the coal, which are then the coal that is then removed. And after the mining is complete, that's either through physical limitation of the coal, either the coal zone is played out, or an economic limitation, meaning it gets too deep or the coal prices are too low to economically remove the coal. They refill the mine site with that blasted rock and in a jumble, and they fill the mine site and smooth it over. This mine site that I'm showing you on this slide is part of the Big Sky coal mine. It's outlined here. The mine area is outlined in black, and these are lines of equal salinity. And so this is showing you salinity in a color ramp of the groundwater. So once the mining is complete and the spoils have been replaced, the pumps, any pumps that were in place to keep the coal dry during production, are turned off, and then the groundwater is allowed to naturally refill the area. And so this is a brand new aquifer. It's the spoils aquifer. It did not exist prior to the completion of mining in this area. And the native water starts moving into the spoils aquifer. And in doing so, in the blasting and then removing and putting the rock back, what you end up with is a bunch of rock material, sandstone, shales, everything that was overlying the coal. Most of it had never been saturated or never fully saturated for any consistent length of time, unless it was below the water table. And for the most part, most of the rock in this area is dry prior to being included in the spoils aquifer. And so that just gives a lot of native salt that had not been previously saturated the chance to dissolve. And so both the blasting brings a lot of salt into contact with water, because water generally has preferential pathways and doesn't interact with the entire rock matrix. And so by blasting it as a brand new, previously unexposed rock surfaces, but also a lot of rock that had never been saturated is now down in the water table. And so, and that was shown in the 1970s when the spoils aquifer was resaturated. The salinity jumped to about 6,000 in some places, even higher. The figure I'm showing you here shows in 1970 a peak of just over 6,000. Um, for uh, for perspective, for comparison's sake, um, drinking water standard is around 1,000 microsiemens per centimeter, maybe less, depending on what is making up those salts. Um, in Gallatin Valley, where MSU is, obviously, uh, the clean gravels in the Gallatin Valley can have SCs, can have microsiemens per centimeter of 500 or even less if you're near recharge, maybe 1,000, but generally pretty low and good quality water. In this area, it's not unusual to have um, natural salinities that are much higher than that because of the prevalence of the fine grained sediments, the shales and the sandstones, and generally the geologic setting tends to be highly saline. So as you move forward in time to the 2010 measurements, you can see that the peak salinity has come down. There's been some flushing, and it's now the peak salinity is under 5,000, so just 4,600. But you're starting to see groundwater in that 2,000 range, which is what we would expect native groundwater in this area to look like, in that 1,700 to 2,000 range. And so in the 50 years shown here, anyway, the 60 years since the mining was complete, we're starting to see groundwater moving in that is not necessarily mobilizing a lot of salt. Where at the southern end, where recharge is focused. However, the question then becomes, where did that salt go? So there's a flushing going on, and that's great, but conservation of mass demands that that salt doesn't just disappear. And so that's where the cruise program comes in, and where the research is focused now is looking at what happened to that salt. Can we find it in the system? Does it make it all the way down gradient to the creek? We are looking, just to give us some context, in the state of Montana, we're looking at the town of Colstrip, which is where the large Rosebud coal mine is, and the power plants, obviously, that are associated with the coal mine. The major coal mining in Montana happens within this larger orange circle. Um, the big open cut coal mines, the two remaining ones that are, well, there's one at Colstrip and then two down where the Tongue River crosses the state line. So my circle is actually a little bit off there, but the Fort Union Formation, which is the source of the coal in Montana, almost all the coal in Montana, is really prevalent within that circle. And so that's the Powder River Basin, and that's why the Powder River Basin is a major source of coal mining for Montana. There are smaller coal mines throughout Montana. There's a small one, an underground mine at Roundup, and even a small mine at Sydney. But aside from those two exceptions, the economic production of coal happens within this orange circle in the Powder River Basin. But zooming in again, you see Colstrip at the top of the screen there. That's the town of Colstrip. And you can see to the west and the south the current disturbed land of the Rosebud coal mine. And that coal feeds the power plants in the city of Colstrip. However, directly south of there, if you train your eye, you can start to pull out of this aerial photograph some of the areas where the ground seems a lot smoother than the naturally rough Fort Union Formation. And so you can see where, if you can see my cursor, where it looks like it's been smoothed over in some of these valleys is reclaimed coal mine spoils areas. The figure I showed you earlier was of the salinity was from directly this southern edge of the Big Sky coal mine. And that was reclaimed prior to the enaction of the Surface Mining Reclamation Act, the SMCRA Act. So it's considered pre-law. So it was reclaimed prior to any standards that were put in place for reclamation. The area that I'll be introducing you to today, and that will be the focus of the crew's work, is just post-law. But the standards for reclamation primarily have to do with surface activities, how the surface is handled, what vegetation is put in, and what standards are expected of the surface expression of the reclamation. However, there is a component of hydrology and an expectation that the groundwater in the reclaimed coal serve essentially the same purpose as prior to mining. And so that is a component of bond release that's unique to Montana, by the way. Other mining areas don't have that hydrologic component to bond release. Also circled here on the southern end is Dobs Coulee. And so because we can't go back in time into the 1960s and 70s and sample the groundwater along Miller Coulee, so this coal mine sits at the head of an ephemeral drainage Miller Coulee. Because we can't go back in time and sample the ephemeral drainage Miller Coulee prior to mining, we're going to use a parallel watershed that is across the drainage in an unmined area, but in similar geology, called Dobbs Coulee. And we're going to use that to serve as our control, which will allow us to differentiate things like maybe pick out the influence of the coal mine, but also help us control for natural changes, environmental controls, different precip regimes that might come in and freshen or not the salinity of the area. So that is just helps us control for the impact from the mining outside of natural variation, for example. And when I say establishing a research site, all that really means at this point in time is that we installed some monitoring wells. We installed 8 of them along that starts at the spoils well at the headwaters here at the head of Miller Coulee. And this is a well that's completed in the spoils and in the first water that we came to within the spoils. And then down gradient along Miller Coulee in that ephemeral drainage, and then further down gradient, mid-Miller well and lower Miller well. Both those wells are completed in the shallowest available aquifer, which accounting for elevation and depth seems to be consistent from the spoils well down gradient through to the lower Miller well. So I'm fairly confident that we're in one flow system. And anyone could probably argue with me, but at this time, I feel pretty confident we're in a flow system with these 3 wells. In order to look at the influence of Miller Coulee on Rosebud Creek, and so Miller Coulee discharges to Rosebud Creek. This little area here is Rosebud Creek. It meets the Yellowstone River near Forsyth. And we put in wells in the Rosebud Creek alluvium above and below that confluence. And maybe confluence is a funny word to use when there's actually no flow in Miller Coulee. Maybe there's a better word. Somebody can email me maybe what a confluence is when there's no flow. But so for now, how Miller Coulee, which doesn't have surface water flow, but it does have subsurface flow, interacts with the Rosebud Creek alluvium will be determined by these 2 wells above and below that confluence. And again, as I mentioned, we have a well in Lower Dobbs Coulee, which would be the unmined corollary to Lower Miller well. Then we have 2 deep wells, both in Fort Union sandstones, one near Lower Dobbs and one near the confluence wells. A monitoring well, in its essence, is just a very specific kind of water well. And so I put a schematic up here that kind of walks through the main elements of what a monitoring well is. And there are a lot of ways that you can construct a monitoring well. This is just one, and it's a pretty common one. You may see other construction in different geologic settings. And there's reasons and good reasons for doing it in other ways. But this is a pretty common way of constructing a monitoring well in eastern Montana. And the Montana water well construction has rules in place for what constitutes a monitoring well, and they need to abide by those rules in their essence. And so a monitoring well is specific that it's only getting water from one very well-defined water-bearing unit. The maximum production is not maximized in a monitoring well. We're really just trying to identify water levels and water chemistry from a specific aquifer. And that can be done, you can isolate that aquifer through this construction technique, which includes drilling down through the aquifer of interest, ideally to the bottom of it so that it's fully penetrated, but often reality steps in and you get what you get, but ideally through the whole unit. And then you put a screen through that water-bearing unit, and then blank and just plain straight PVC to the surface. And the screen is surrounded by sand or gravel fill, and that keeps the aquifer material away from the screen. And that's important, especially in eastern Montana units and anywhere you have a lot of fine grain silts and clays, because those clays can migrate toward the screen and form a caking layer, and your well will be ruined, for the lack of any other term. A well-constructed monitoring well can last for decades, and we have wells that have been consistently monitored for since the 60s and the 70s, and so for decades, a good well can last for a really long time. And so it's important to put the thought in and to put the effort in to make a good well at the beginning. And then once you've filled the annular space around the screen, you fill the remaining annular space with either bentonite clay or cement is sometimes used, but bentonite clay is more common, I guess, at this point, especially when you're using PVC. You can have issues when you use cement and PVC. But bentonite clay is a 2-to-1 smectitic type clay, and it's hydrophilic. And when it is hydrated, it swells and forms gumbo. I'm sure a lot of Montana, anyone who's driven around Montana is familiar with gumbo and knows how sticky and frustrating it can be to deal with. And so it forms this like very secure barrier between the ground surface and the aquifer, and that's what we want to do. We want to protect the aquifer from any activities at the surface. And it also seals off any additional water. If you have an aquifer above the aquifer of interest, you can effectively seal off any water from that unit using bentonite. The recommendation is also for steel casing at the surface, and that helps protect the PVC. PVC wells left unprotected at the surface tend to be a magnet for being run over. They seem to have a target on them, in my experience. Not intentionally, at least I hope not. They just happen to be accident prone. And so putting steel at the surface helps protect that PVC both from being broken, but also from fires. And the last thing, in this area, fires go through on a fairly frequent basis. And the last thing you want is your PVC casing to melt down. And that just, any trauma to the well casing can be a pathway of contamination. And that's the biggest concern. What we want to prevent is contamination moving down either the wellbore or the casing, if it's damaged, into the aquifer. And so all these protections are in place to maintain the quality of your aquifer. I have a color gradient here that's supposed to represent Fort Union stratigraphy. I don't know if anyone else sees it that way, but that's what it's supposed to look like. And Fort Union is it's a major geologic unit in eastern Montana, and of course the source of most of the coal that's commercially produced in Montana. And it's interlayered shale sandstones and coals. However, we only have the two bedrock wells that we installed for this one, for this study, two of these Fort Union wells. The rest are all shallow wells that are anywhere from 20 to maybe 40 feet deep, and they're completed only in the unconsolidated, either the colluvium, which are the fine-grained sediments that move off of the surrounding hills, or alluvium in the case of the Rosebud Creek alluvial aquifer. Here's an example of a well screen. This is about 10 feet of well screen that we put into the mid-Miller Coulee well, and a blow up of an example of a factory slotted screen. This is pretty fine screen. It's sized for the geologic material we thought we were going to be interacting with, and for these fine-grained sediments, it's important to have a fine screen. Other screens are available if you have a different aquifer or if you're trying to maximize production, but that's usually not the goal in a monitoring well. This is an example of a tricone drill bit, and I am not an expert in drill bits or drilling by any means, but the bit can be chosen based on the material, the geologic material you'll be drilling through. However, despite running into a whole bunch of different drill settings, everyone seems to choose the tricone bit, and so that's why I picked a picture of that for this presentation. That seems to be a pretty popular choice, at least in eastern Montana. We used a dual rotary rig on this this drilling program, and a dual rotary rig is unique to other types of drilling in that the bit turns one way and the casing is locked into a Kelly table and turns the opposite way. And so the drill bit is drilling just ahead of the casing, turning, and the casing is also turning. And that makes for a pretty fast and keeps the borehole pretty straight and true, which is nice, especially if you have to install a pump later. And this was my first time sitting a rig that was dual rotary, and I was impressed with how slick it all worked. In any type of setting, the drill cuttings are moved up the borehole in the casing using compressed air, or if the drill cuttings get too sticky and aren't making their way up the borehole very easily, they can add water if they haven't already encountered groundwater in the system, and that flushes the drill cuttings out of the casing, and they're discharged from that hose. You can see the gentleman standing by the discharge hose. And this is actually a little video, and when I say it goes fast, you might question it because you don't actually see any progress in this video, but everything in geology is on a kind of different time scale, so fast is relative. But it does give you a feeling for how loud it is to sit on a drill rig, and it just speaks to the importance of correct PPE, both protecting your hearing, protecting your head when you're out working on installing monitoring. Here's an example. This is shows you the setting of the spoils well, and you can see maybe in a little more detail that smoothness that I was talking about, how that the spoils has been bulldozed into kind of a smooth wave that washes up on that unmined sandstone outcrop. This is an example, because this is spoils, it's a mishmash of everything that used to be in place. And just standing in one spot on the spoils, I was able to pick up a whole array of different types of geology. Like there was sandstones and shales, different colors. There's some clinker represented here. Some of those darker red ones are clinker, which is rock that's formed when coal beds naturally catch on fire and melt the geologic units above it, turns it into kind of a lava-y, vesicular, interesting rock and difficult to drill through. But lots of interesting geology just standing right there on the coal spoils. Moving down gradient, the mid-Miller well is in a narrow part of Miller Coulee. At this point, it's probably a quarter mile across. Um, and again, like just completed in the first water that we came to in the colluvial aquifer. Down gradient, again, this is the lower Miller well. You can see that the valley has opened up quite a bit. It's probably not quite a mile across at this point, but still the water was found at approximately the same elevation if you account for elevation loss. And but the production picked up as we got down lower. So this will actually produce pretty well, on the order of maybe 20 gallons a minute. We moved down to the alluvium. This is the alluvium of the Rosebud Creek, and Rosebud Creek looked like this in late August when we were there. Rosebud Creek is not usually very big. It is almost always under 100 CFS, and at this time it was well under 100 CFS. But like a lot of creeks, like most creeks of this size in eastern Montana, it's really flashy. It drains a huge area for the size of the creek. And so focused thunderstorms or spring thaw can bring this creek to flood stage very quickly. It goes up and down really fast because the thunderstorms can be very isolated in this area and bring those water levels up very quickly. Lower Dobs, this picture is actually from the upper area where we drilled the deep well, and it just gives you a good perspective of what the landscape is like south of Colstrip. The lower Dobbs well was a Fort Union well that went through a whole bunch, went through 100 feet of Fort Union. And the Fort Union is great because it's so variable. In 20 feet, we started in this kind of perched terrace aquifer, which were well-sorted rounded gravels, or I guess not that well sorted, fairly poorly sorted, but rounded gravels. And then a red sandstone, a yellow sandstone, a coal, and then a shaly coal, and then a nice massive gray coal, all within 20 feet. And that's what makes drilling in the Fort Union so fun. You just get a whole bunch of different geology in a short length of borehole. We don't have any samples yet from these. However, when we were developing, which is when the driller blows water into the well in order to bring water out, and it also helps serve to push the drilling fines away from the borehole, which helps increase the connection of the well with the aquifer, and that's our ultimate goal, is to be looking at the native water. While we were developing, I was measuring the salinity, and you can see that the salinity kind of marches down from a high at the spoils aquifer of 4,600, and as you get lower, 43, to lower Miller Coulee, not quite at the mouth, you've got 3,100, and I'll put a big asterisk next to these values because it is just during development. There's going to be some source of error in the fact that the wells haven't been fully developed at this time, and so the error is probably at least 10%, probably much higher than that. However, I do think we can confidently say that there seems to be a salinity gradient from the spoils down gradient on Miller Coulee. How that compares to what I would call native water. The native surface water at Rosebud Creek was 1,600, and then the native groundwater at Lower Dobbs was right around 2,000. Those are values that we expect to see and have seen at the other study site on Big Sky Mine. So I think we're seeing some elevated salinities, possibly due to the mining and the reclamation. Looking at how Miller Coulee, the groundwater in Miller Coulee interacts with the alluvium. For the lower confluence site, I would expect the salinity to fall somewhere between Rosebud Creek's salinity and that lower Miller salinity, and it does. It's kind of right there between the two, and it might show a mixing of the groundwater from Miller Coulee and the alluvial water associated with Rosebud Creek. However, um, I would not have expected to see the elevated salinity at that upper site. And of course, if everything happened as expected, life would be pretty boring. And so that 3,800 in um, the upper confluence well, I would have thought it should look more like Rosebud Creek or 2,000, like the lower Dobs groundwater. Why it's as elevated as it is has generated more questions than answers at this point, and so that will be a source of some investigation in the future. And it could mean that we just weren't far enough up gradient and that we're still within the influence of Miller Coulee. We also did the two deep wells, and those were right in the range of what we usually see for Fort Union wells. The question for the deep well by Rosebud Creek would be, is the salinity from that bedrock well influencing the salinity of the shallower groundwater? Could it be a source of salinity at lower Miller Coulee? The short answer is yes, but the longer answer is I don't think so, because looking at the potentiometric surface, I don't think that there is an upper gradient at that point. However, that's going to take a little more QA, QC on my part to be able to definitively say that and to know. And then hopefully the geochemistry and some of the other investigation we do will help show whether or not we're seeing any influence from those bedrock units into the shallow system. Next steps include sampling all these wells for isotopes of sulfur and oxygen of sulfate, because we want to fingerprint the sulfate itself. And also looking at the strontium isotope ratio as another fingerprint, because strontium is conservative. It's not fractionated. The ratio is not fractionated in biological microbial processes. However, and it's not fractionated in precipitation or evaporation, whereas sulfate is. And so precipitation of sulfate salts or sulfur-reducing bacteria can fractionate those. And so doing both in concert helps us control for some of the natural processes that might be working on the sulfate isotopes. And then we're also going to be looking at major cations and anions and the trace metals, because that shows us a lot about the geology that this groundwater has been interacting with and where some of those salts have been coming from. And because I don't have any real data to show you, I'm showing you somebody else's real data. These are my colleagues from Tech, from Montana Tech and the Bureau of Mines, their research on the Great Falls coal field, looking at sulfate isotopes. The Great Falls coal field is no longer produced, but because it is more pyrite rich, it has a tendency to generate acid and acid mine drainage, whereas eastern Montana coals don't have as much, if any, pyrite, and so generally don't become acid producing. But they were looking at the potential for the acid mine drainage in the belt and the Stockett-San Coulee areas to interact with the limestone aquifer that's used extensively through eastern Montana, the Madison limestone. And they were able to show the influence of that sulfate isotope from the AMD, which you can see in red, pretty distinctive compared to the upper end of the recharge area in Madison, in the Madison aquifer. And you can see a pretty nice mixing line in these domestic wells that are completed in the Madison aquifer, looking at how much sulfate might have originally come from this AMD. And what's interesting and what's so great about groundwater and the limestone aquifer is that a lot of the characteristics about AMD that are of particular concern, meaning the acidity and the high metals, are buffered really quickly by the limestone aquifer. The acidity, the pH is buffered to near neutral fairly quickly, and that in turn helps those metals fall out of solution. And so the remaining evidence, so a lot of the groundwater is still within drinking water tolerances, a lot of it. And so really the only evidence of the AMD in the aquifer is the sulfate isotopes. And so using this as a tracer, they're able to see pathways within the recharge area that where the AMD is interacting with the aquifer, even though major ion chemistry is hidden from them. Real quickly again on the same study, but they put it into a regional perspective, and they showed that they believe that there are actually 3 different sulfate systems going on. There's the unimpacted path A, where the sulfate from a recharge interacts with the sulfates from naturally occurring evaporites on the top of the Madison, and then the groundwater gets pulled off of path A at different points toward AMD, depending on when the AMD, where along the pathway, along the flow pathway, the AMD interacts with the groundwater. And so you end up with either path B or path C. So some really interesting work that should be published here in the next few months. I think it's very close. And so here's some work that I did showing the strontium isotope capabilities in the Powder River Basin. And I don't want to go on too much longer. I see we're getting a little short on time, but the sulfate isotope ratio, or so the strontium isotope ratio, excuse me, in the Powder River, as the Powder River crosses these numerous small coal aquifers, the ratio within the river of the strontium isotope becomes more and more similar to the strontium isotope ratio of the coal groundwater. And this is important because it's very hard to show groundwater contribution to a river like the Powder River when you can't really measure a gain in the surface water, because the water is continuously being used by for agricultural reasons. It will be diverted for irrigation. There's a lot of subsurface irrigation, which means crops that are down using groundwater naturally. So a lot of transpiration demand. And also the valley tends to widen and narrow, and so you can lose the surface flow into the valley alluvium or gain it from the valley alluvium. And all those things mask any contributions from groundwater. And so strontium and these other isotope tracers are a good way to identify groundwater contributions when you can't see an increase in flow for whatever reason. A similar story on Otter Creek. You'll remember Otter Creek was a target for coal development beginning in about 2010. And again, Otter Creek, the strontium isotope ratio, as it crosses these pretty significant coal zones, the knobloch coal, which was going to be produced, as it crosses the knobloch coal outcrop, also gets a strontium isotope ratio that progressively becomes more similar to that of the coal groundwater. And there's a lot going on in this figure, and I apologize, don't have time to unpack it all for you. But in general, the strontium isotopes and in this study, carbon isotopes were both effective tracers here. One more strontium isotope figure, only because I think they're just so useful. But this shows how strontium isotopes can identify different physical processes that happen in a mixing situation. In this case, this is coal groundwater that's brought to the surface and discharged at the surface through the coal bed methane mining process. They just bring a lot of coal groundwater to the surface, and in this case, discharged it into some ponds. And not going into too much detail, it does show both precipitation and dissolution of salts, but more important to this study, it effectively showed the mixing of the groundwater with the surface water and the groundwater, the coal groundwater with the naturally occurring, the in-place shallow groundwater. So all these previous studies and the ongoing work by my colleagues help me have confidence that I think we'll be able to be similarly successful in the future. And here's where I take just a minute to get on my soapbox. But first, I have this video that I like to play. Can you feel the 100-degree heat? Because I can. And I mostly just play this to give my colleagues who work in HEPA filtered clean rooms, I like to give them the willies by showing them this, my sample collection process. But this is just a segue into to my soapbox that I tend to get on every once in a while. And it's just to say, you know, this is what I believe is an audience mostly of MSU students, undergrad and graduate students. And if you're a student who's looking for a career pathway, and you, like most people, envision science as the picture here, I mean, you can't be blamed. This is how science is portrayed in most common media, in most, you know, children's books. Scientists have pipettes and flasks and you know, or balances and measure things in micrometers and milliliters. Um, and if that's not for you, that's okay. I spent my time in a HEPA filtered clean room, and I'm glad I did because I think it makes me a better field scientist to know what happens to the samples after the fact. However, I would not trade that world for my current lab bench, which is the back of my truck. And I think a lot of students coming from backgrounds in Montana may feel more comfortable in the back of a truck than in a clean room situation. And I want to take this opportunity to let you know that there is a role for you too. Um, Science needs everyone, and it needs people who are comfortable driving four-wheel drive on two-track roads, and it needs people who have the attention to detail to measure things in milliliters and micrometers. But but science needs all kinds, and if you're not the kind to feel comfortable in nitrile gloves, there's still a pathway for you. I'm off my soapbox. I'm going to finish up by showing you a video from the last well. This is the Dobs deep well in a massive sandstone. Oops, go back again. And it ended up producing by the end of the day, like probably close to 60 gallons a minute. And in eastern Montana, that is a gusher. And that kind of production just makes the whole trip and the whole week in 100-degree weather so worthwhile to see this kind of successful well. Just makes it so much fun to get a good well like that. That brings me to the end. I want to say thank you real quick to my research assistant, Allie. She's a senior undergraduate at Rocky Mountain College, and she's just doing great things with her geology program there. And that's where I will leave it. There's a couple minutes for questions, I think.
Yeah, thank you so much, Letty. We've got a little bit of time before 1, so again, if you have any questions, please feel free to either enter those into the chat function or feel free to unmute yourself and ask those directly as well. But a big thank you, a round of virtual applause for your presentation. It was wonderful.
Thank you. I can unshare my screen and then I can probably see the chat.
Yeah.
But if there are further questions, it might be hard to get it back. But then I can probably see when people virtually raise their hand. Right.
I've got a question. Can you hear me?
I can hear you. I can't see you.
Hi, Lydia. It's Wyatt.
Oh, hi, Wyatt. Now I can see you. Yes.
I love your enthusiasm for the well activity. That was really fun to see. That isotope signature of sulfur. I wonder if people have investigated whether that is also can be tracked through different components of the ecosystem, both groundwater and surface water, microbes, vertebrates, fishes, birds, things like that. Do you know anything about that?
I haven't dug into the literature for biological uptake and sulfur identification, but it sounds um, definitely like a possibility. I don't know if anyone is looking into that. Um, I guess one thing I want to mention is that part of the challenge that we're going to find here is a scalability. What we're looking at, the reclaimed coal mine I showed you was a couple miles across, all in, which is a fraction of what is currently disturbed in Montana. And so the sulfate story that we're going to see is going to be kind of like looking for a needle in a haystack. And the challenge that we need to really concentrate on is how does that scale to the current disturbed ground that we see both in Montana, which is a fraction of what's disturbed in Wyoming. And so, and all those water systems all feed, Wyoming's watersheds feed right into Montana, which feeds right into the Yellowstone. And so we need to be thinking not necessarily about how Big Sky and the sulfur story at Big Sky is going to be the environmental question. It's what can we learn that we can apply to these larger systems? And so, like your question about following it into the biological realms, I think will be more more uh, possible when you start scaling up like that. I just want to say, like, if we don't see it in this system, that doesn't mean it's not possible. Okay. Because it's so much smaller than the larger systems that we will be dealing with in the next decades.
Right. Okay. Okay. Thank you.
Awesome. Do we have any final questions for Liddy?
Hi, Liddy. This is Greta Gansauer. I'm a student with Julia Haggerty. I'm also on the Cruise Project in the social science world. And I'm just wondering if you can, and I apologize if you mentioned this, but just orient me a little bit to just the geography of the communities around there. And I'm wondering how, if you're aware of source water for communities and how this, I don't know, might affect them if they're getting water from these shallower aquifers, or just if you have any sense of source water around there.
It's a good question, and it's one that's facing Colstrip really pertinently right now, because so the major communities it's really Colstrip. Some of the like Lame Deer and some of the smaller communities on the reservation have some mining up gradient from them, but nothing on the scale of Rosebud Creek mine. Outside of those communities, it's mostly just individual domestic wells, which the Rosebud Creek side of the watershed that we're looking at does not interact with the Armel side, which is the Colstrip power plant issue. So Rosebud Creek doesn't have the contamination that the city of Colstrip is dealing with. Colstrip does have some challenges facing them in the very near future because their source water is currently the Yellowstone River, which is piped a long way, and that is funded by the power plant. And the water right, as far as I understand, is owned by the power plant. And so when that source of money and that source of water is no longer present, will Colstrip be able to continue to use the Yellowstone water and and fund the cost to get it down to Colstrip? Groundwater in this area is generally hard to come by on the scale necessary for a city the size of Colstrip. So I guess that's about what I know. Like the majority of people are on individual domestic wells. Sulfate is a secondary standard for human drinking water, so that shouldn't be too much. And the treatment to get groundwater from 2,000 to 3,000 microsiemens per centimeter down to 1,000 is not cost prohibitive for most people. It's a pretty easy treatment. So for that, I think it will be fine. I think Colstrip is really where the discussion needs to focus in the future.
Great. Thank you very much.
Mm-hmm.
Awesome. Well, we are right at 1 o'clock, so let's go ahead and wrap up the seminar. And again, a big virtual applause and thank you to Liddy for your presentation. It was wonderful, I guess. But just as I said at the beginning for folks, we did record today's presentation, so you can find that. I hope to get the video posted on the IOE website later today, which if you navigate to montanaioe.org/media/videos, you can find it there. I put the link in the chat box. And just a plug for next week's seminar, we'll have 3 speakers actually then presenting next Wednesday at noon on a Montana Conservation Atlas. So thank you all again. Thank you, Liddy, and I hope everyone has a wonderful rest of your Wednesday.
Thank you.
Thank you. Bye.
Bye-bye.